Hi, welcome to the talk on Physics of Language Models, Part 4.1, Architecture Design and the Magic of Canon Layers. So 4.1 is a standalone paper in the series of work. It does not require any prior knowledge from other parts of the series. However, Part 4.1 alone already contains too many results and many methodology lessons, so I decided to subdivide the talk into two separate videos. The first video, the previous one, that I call it Part 4.1a, actually covered why real-life pre-training is noisy and why it is absolutely necessary to build your own synthetic pre-train playground in order to study an architecture's true capability. So that talk was especially interesting, I think, to theoreticians and researchers who really care about how I built the specific tasks and why they are particularly good at differentiating different architectures' capabilities. So that was the previous talk. In this second video that I call it 4.1b, I'm going to cover once you have the playground, then what architecture principles can you derive from it? So this one I think will be especially exciting to apply to researchers who care about, say, what architecture changes do I need to make in order to implement tomorrow's next generation of the AI models to make them reason deeper, wider, or just perform better in general. So I'm going to make the second video self-contained by spending just one single slide on recapping what was the synthetic playground. So in the previous video, I introduced the 5 synthetic tasks. So each one of them actually isolates one different atomic skill that we hope the language model to be able to perform. So we want the model to reason deep, we want the model to reason broad, we want the model to hold enough factual pieces of factual knowledge, and we want the model to be able to perform multi-hop knowledge-based reasoning, and we want the model to be able to do structural reasoning. So those are 5 different tasks. Each one actually covers a different kind of orthogonal dimension about the skill of the language model. And for each one of them, we design the tasks so that you can test an architecture's performance after pre-training on such a task. So for 4 of the tasks, we actually color-coded them and introduced the following, what I called mini-scaling law. So in one of the dimensions, the x dimension, I'm going to vary the size of the model. So the maximum model size I ever need to look at, very importantly, is at most GPT-2 small scale, so 100 million parameters. And you can even try smaller architectures such as 8-layer, 512 dimensions. And in the y horizon, very importantly, you can now vary the difficulty of the data. So because we have synthetic pre-trained data, so you can actually design parameters that will control, for instance, how deep the model is going to reason and so on. So you can control the difficulty of the data. So in such a way that whenever you have a model architecture family, you can evaluate, for instance, how well does it perform in this 3x2 kind of 3x4 mini scaling law. So if all the numbers, all the accuracies are kind of high, then that implies that the architecture family is good in terms of reasoning depth. But if all the numbers are kind of in average pretty low, very dark, it means that the model, the architecture is not good at deep reasoning. So that was the concept, and that was 4 out of the 5 tasks. For the last one, this knowledge capacity, we have to evaluate it a little bit differently. So in this task, we need to very accurately measure for an architecture family, then how many bits of factual knowledge can it hold per parameter after sufficient training. Okay, so therefore, over there, we need to basically, vary the model size in a much larger range in order to compute this frontier line more accurately. But the good news is, once again, thanks to this synthetic task design, it's not real-life data that is too messy, so it's our synthetic, perfect data. Then you can actually, compute this frontier line without ever needing to look at, models that are larger than 100 million parameters. So that turns out to be more than enough for you to, very accurately measure this frontier line. So therefore, if you're comparing 2 different architecture families, transformers versus something else, then you can see which one of them has this line being higher than the other one. And if higher, it means this architecture is generally better in terms of how much knowledge it can store. And also similarly for other skills, if you see it's generally much brighter comparing to another 3x4 mini scaling law of a different architecture, then you'll claim that this one is good in terms of knowledge manipulation, for instance. So that was the synthetic Pretrain playground that we built from the previous talk. So in this new video, I'm going to tell you that once you have the playground, then what architecture principles you can derive. So I'm going to actually organize the results into a family of 12 different results. So before I even start, let me remind everyone about a simple fact, that is like, how does transformer work, right? So transformer works in the following way. That is, once you have token in this time horizon, and say that you have maybe a 24-layered transformer, then you forward each token in this depth direction, right? You forward it for 24 times, each for 1 layer. But very crucially, like whenever you want to have 2 different tokens to communicate with each other, you have to rely on this so-called attention mechanism that can help you to very accurately, for instance, bring the information about 1 token to another place, but it's also very expensive. And very often, if you think about it, all I want to do is maybe just to understand what is the token in front of me, or what is the token like what are the 2 tokens in front of me. So if you want to implement this like very simple operation, then with the current design of transformer, you have to rely on this very heavy attention mechanism. So let me give you at least like 3 different reasons for why like this type of operation is very needed in practice. So number 1, the most naive reason is because even an English word, I would say maybe at least 50% of them actually spans multiple tokens. So therefore, like already on the input level, you want each token to be able to read its previous token in order to understand which English word I'm talking about, right? So that was a naive reason. But a slightly deeper reason is with respect to this so-called associative recall. So people know that transformer or attention are good at performing associative recalls. So what is associative recall? Let me remind everyone. So whenever like you have a bunch of tokens, for instance, then whenever you see a token A or token B, and if you see A again, then you want to predict the next token to be B. So this is the task called associative recall. So let me actually tell you that associative recall requires 2 layers of attention to implement it. So if you opened up like a textbook that talks about transformer, it's going to tell you like attention is really designed to perform this task. But what I think like maybe half of the researchers probably don't know, I want to make sure everyone is on the same page, is that this cannot be implemented if you only use 1 single layer of attention. So for instance, you may think that, can I attend this A to this A? Yes, you can. But over there, there's no information about B. If you do like an autoregressive, like left to right kind of language model, then there's no information about B that can be stored here. So therefore, like just attending it once doesn't solve this task of associative recall. So you have to do it twice. So the first attention has to be able to store the information about A to its next token at this position. And only after that, it allows you to perform this kind of standard attention. That is, you can use a key of A to retrieve the value of B by attending to this position. So therefore, like associative recall actually needs 2 layers of attention. So this is not only just theory, you can also test it in practice. You can try, for instance, a simple task of fully copying like 500 tokens, and you can try this at home. If you use just 1 layer of transformer, for instance, using the rotary positional embedding like rope, then like pretty much like you can't get almost any good accuracy unless your hidden dimension is very large, like 128. So this is because like 1 layer transformer turns out to be Turing complete. You can use 1 layer transformer to implement everything, but maybe not efficiently. So you see that if you use a 2-layer transformer, you only need the hidden dimension to be like 16, for instance, to be able to like learn this task of full copying of 500 tokens. So therefore, like this is why I put a double quote, because it's not exactly like needs 2 layers. It's like if you want to learn it efficiently, you need 2 layers of transformer or 2 layers of attention. So this is something you can test it even at home. But the lesson we learned from here is that even this kind of simplest task of associative recall, you can see that it requires actually this task of reading what is the token to your left. Okay, not to say like even harder tasks. And a third kind of dimension that I think it's very necessary to sort of read to your left is because you can equivalently like increase your thinking space. So think about it. If you always work in the dimension of D, like hidden state of size D, then you can only perform operations like within this D-dimensional space. But if you can have very easy access to the previous, say, 3 tokens, so this can effectively like increase your thinking space to be 4D dimensional space. So you can perform like 4D dimensional operations much more easily just because of this like easy access. So for all of those reasons, we actually want to have architecture changes to, for instance, the transformer architecture to allow it to perform this kind of, read maybe 1 token or 2 tokens ahead of me, like very cheaply without invoking the attention mechanism. So this is the concept I'm going to introduce in result 1. That is, I propose to add some maybe very cheap architecture components in order to support such kind of horizontal information flow. So this is what I call Canon layers. Okay, so the idea is very simple. Whenever you're at maybe some time horizon t and with hidden state maybe ht of maybe dimension m, then you can, for instance, read what were the previous like 3 hidden states and then perform a linear combination of them. So those are like coordinate-wise multiplication, and then call the resulting vector ht prime. So next, like whenever you forward to the next layer, to the deeper layers. So in the past, you just forward ht to the next layer, but now you use ht prime to forward to the next layer. So this way, like you can, add such horizontal information flow, very easily, like using such cheap, like linear operation. So there are 2 details that I'm missing here. Number 1 is where to add such horizontal information flow. The second one is how to implement this. Okay, one thing at a time. So where to add this? In each of the transformer layer, for instance, some people call it a transformer block. There are actually 4 sub-layers. So the first 2 of them corresponding to the attention layer, and the second 2 corresponding to the MLP, for instance, gated MLP layer. So this is an example about how it performs. For instance, you start from a hidden size of dimension D, then the first layer of the attention is going to expand it into query, key, and value vectors, so therefore of dimension 3D. And after performing attention, it projects everything down back to dimension D. And now the first layer of the gated MLP, for instance, up projects this vector into dimension 16D over 3, and then down projects it back to dimension D. So that was like roughly like how a transformer block, or you can call it a transformer layer, work. So this gives rise to basically 4 very natural points where like you can add such horizontal information flow. So if you add it only at point A for each layer, then I call it Canon A. If you add it only at position B, then I call it Canon B, and so on. So if you add all of them, say for every single layer, you add at points A, B, C, D, all of them, because why not? Then I call it full score Canon or Canon A, B, C, D. So the name canon really like is borrowed from music. So in music, a canon is when the same melody is played multiple times with different delays. Like one voice starts, then another one comes in 1 beat later, another one comes in 2 beats later, and so on. So when you add all of the delayed versions of the pieces together, you get a final piece. So that was the notion of canon in music. So I'm borrowing this name because here, like, it's essentially doing the same. Like you're like just adding such kind of delays of 1 beat and 2 beats and so on. So that was the name and where to add the kind of layers. And the next question is how to implement this. So there are at least like 3 different levels of details regarding like how complex you want to make the Canon layers be. The simplest, the most naive implementation is to actually make those weights just randomly chosen and then fix them throughout the training. So of course, like for each like different layer, like point A, B, C, D, or each big layer, then you want to have a different random seeds. But once like they are randomly initialized, then like you don't change them and just leave them there. So this turns out to be already highly effective. So I showed all the experiments in the paper, but I'm not going to include this part in the talk. So this means that you probably don't even need like very complicated implementations of the Canon layer, and they can already work very effectively. And in all of the 5 synthetic task dimensions, you're going to see that this is going to boost your model's performance. But if you ever think about randomly like fixed weights, then in practice, that's maybe you should maybe like actually make them trainable, because like in terms of the computational time and also GPU memory, then it's not actually too much different like if you make them trainable or randomly fixed. So if they're trainable, then this is the so-called one-dimensional convolutional layer, or Comp1D. And some people like in this setting call it depth-wise Comp1D or causal Comp1D. So the TriDel has very nicely implemented the CUDA implementation for this very efficiently. And this was very firstly introduced in their H3 paper. So this is called like Comp1D or depth-wise or causal Comp1D. But we want to advocate a slightly different implementation to this. Namely, we want to add a residual link on top of the causal Comp1D. So as we will see, like in a lot of experiments today, that this residual link turns out to accelerate training and makes it very stable in terms of like where you want to integrate such Canon layers to your architecture. Because think about it, like at random initialization, the causal Comp1D part is going to give you like almost a zero contribution, like at least it's totally random with expectation 0. So therefore, like at random initialization, your model is kind of functioning as if like those like horizontal information flow doesn't exist. So therefore, like at the very beginning, you're really fully respecting to the original architecture's functionality flow. And only after training starts, then the model starts to be able to recognize like, oh, like those Comp1D exist. So therefore, I can make use of the horizontal information flow if needed. So therefore, like this way of adding the residual link is going to make your training actually very stable. So in all of the experiments I'm going to show today, that it never hurts the performance of the model and it only helps. Okay, so this is like the implementation we're going to advocate today. But you don't have to stop here. You can, for instance, consider like more complex forms of the Canon layers, like making the weights to be dynamic, to be, for instance, some learnable functions on top of the hidden states by using some maybe low rank computation or some gated computation and so on. So this is definitely less computationally efficient. And I tried actually a little bit in some smaller scale, like it doesn't seem to be very necessary to me. So therefore, like today, I'm going to actually mostly only focus on here, because I want to advocate the fact that it's in general, like the more Canon layers you add, the better. But as opposed to like you want to make those Canon layers like more complicated in practice. So this is what I'm going to focus on today. But I really want to make a remark here that is, in the end of the day, Canon layers do not need to be implemented using Comp1D. So like depending on if you're using TPU or GPU, like you can in the end of the day you can invent like even cheaper ways to implement such horizontal information flow. So what's important is that you make the information like flow horizontally instead of like what specific implementation it is. But for the reference of this talk, I'm only focusing on this particular implementation because I want to show you basically where to add such Canon layers and how to, like, what are the contributions of such Canon layers. So I'm going to leave it a future work regarding like how to make it like implement like faster or like more TPU or GPU friendly and so on. So that was result number 1. So I introduced this notion of Canon layer, and now like let's see like how it's going to perform on top of the transformer architecture. So let's take the original, the vanilla transformer. So throughout this talk, I may interchangeably use the word like transformer or rope or llama to actually mean the same thing. That's the original transformer, but plus the rotary positioning embedding and plus like gated MLP. Okay, that's like the standard kind of transformer that people use nowadays. So this is how it's going to perform like under our synthetic playground. And by the way, we have 5 tasks. The one that's missing here is the knowledge capacity. I'm going to show you like starting from result 5. So for now, I'm just focusing on 4 of them because they're, you know, all look similar like in terms of the minute scaling law. So now let's see the very simple thing that is once you introduce the Canon layers on top of rope, and how does the performance change? I'm going to change that. I'm going to tell you that it's going to change dramatically, and to an extent that we can even precisely measure how much gain there is. So in terms of the first task, like reasoning depth, So that was the task I introduced in the previous video, and the very high-level idea is that I give the model like a random permutation and then ask it like what is the kth successor of a given node A, and this requires the model to perform some k-hop reasoning, and it cannot use chain of thought. It has to directly answer the question. So therefore, it's some k-hop reasoning task. And it turns out that if you use the vanilla transformer, the model cannot even perform like 4-hop reasoning. So here, like there are two accuracies. The first one is 8-hop, the second one is 4-hop. So you see that the model can't even do 4-hop. But once you add the Canon layers, in like at least half of the cases in this mini scaling law, you see that the model can perform even 8-hop reasoning. So therefore, like I declared like a 2 to 4 times increase in terms of the reasoning depth, just after simply like adding those Canon layers on top of your transformer. So that's in one of the task dimensions. The other one, say this one, is the task of knowledge manipulation. So it's basically about an L-hop reasoning task based on knowledge. So you have to retrieve knowledge like L times and then perform some operations using some mental reasoning skill without chain of thought once again. So now the important thing is that what used to be like the accuracy pattern with respect to 10-hop reasoning is now like the same. The numbers look almost identical to this row, which is now 16 hop reasoning. So therefore, like you're essentially having a 60-time increase in terms of the knowledge manipulation length. That is the number of hops that you can manipulate knowledge. So therefore, like this is also a solid increase in terms of your reasoning capabilities, in terms of knowledge manipulation. And you can similarly like quantify it in other skills, for instance, hierarchical structure learning. So in this task, you can, for instance, read vertically, and what used to be the accuracy pattern for the GPT-2 small scale, that's 12 layer and 768 dimensions, is now almost identical to still like 12 layers, but only 512 dimensions. So this is only half of the size in terms of the training parameters, comparing to GPT-2 small. So therefore, like you can declare a 2 times reduction in the model size. And you can similarly like derive something here for reasoning breadth, and I'm not going to read the details. So overall, like you see that with synthetic pretrain playground, you can even kind of measure like how much you can gain like by just performing one architecture change. So this is like a very clear thing, and comparing to especially the real-life pre-training accuracies, which are just single numbers and also very noisy. But here, like you can see this kind of a very big jump of the performance. But why does this happen, right? So I introduced this Canon layers, right? And why in the hell, like just by suddenly adding those Canon layers, for instance, my model can suddenly like reason much deeper. So this is some result. I'm going to call it result 2.1. It's not yet included in the paper, and congratulations if you're listening to this talk. So this is the first time I'm kind of introducing the reason behind the scene. Okay. So some people may think that Canon layers maybe perform well just because of the first layer, because maybe I want to know maybe some of the English words span multiple tokens and so on. But there's a very simple way to refute this. That is, you can actually try to add Canon layers, but only to the first transformer block. But for instance, maximally at positions A, B, C, D. So I tried this. This is not yet included in the paper. I will put them online like very shortly. But you see that it's going to give you a little bit performance jump, maybe for the largest size of the model for the simplest data, but it's nowhere close to like you add all of the Canon layers at all the transformer blocks. So therefore, like you really want to add Canon layers in all the transformer blocks, in all the layers, kind of maximally the possible. But why is it so, right? Why do I need Canon layers, for instance, at a deeper part of my transformer, of my language model? So this is precisely what I'm going to explain to you. In order to see that, let me actually give you this like closer look about how, for instance, the original transformer perform versus the one transformer but adding the Canon layers. So if you look at just one hop reasoning, the two curves are almost identical. So they even reach, for instance, about say 98% accuracies at around the same time. So therefore, like adding Canon layers does not impact your one hop reasoning. That is the simplest like information retrieval. So therefore, this is another evidence that Canon layers is not really important, for instance, on the first layer. So what it turns out to be helping is actually this hierarchical learning procedure. That is, it's going to make the model like learn 2-hop or 3-hop and 4-hop and so on. So this graph, like you can see, even up to 16-hop, it's going to make this hierarchical learning actually perform much faster. So in this graph, like for each hop, like say 1-hop or 2-hop, I'm plotting 2 curves. So those are actually 2 out of the 2 best learning rates out of the 4 learning rates that we swept. So therefore, like it's like you see, like it doesn't matter which one you use. Then if you use the Canon layers, then all of the the hierarchical learning like perform much faster and so on. But this is once again the phenomenon, and why did this happen? So in order to explain this requires me to introduce a little bit about our theory work back to even 5 years ago. So over there, like we tried to tackle a very deep question over there. That is, why does deep learning perform deep learning? So this is a very trivial question. That is, you can build, for instance, a very deep network, right? But it doesn't necessarily mean that in the end of the day, your Sc.D or Adam or Mun optimizer is going to actually learn a deep function. So there exists many counterexamples from the field of learning theory. So this is the picture I'm going to repeatedly show you today. That is, I think existence is cheap, but learnability is everything. So you can, for instance, make your architectures arbitrarily complex, make it, do a lot of wishful thinking there. But in the end of the day, what say Sc.D learns could just be a very simple function. So therefore, in order for deep learning to really learn a very deep function, what ends up needing is actually this kind of data hierarchy. That is, your training data has to not only contain hard data, but also medium level data and easy data kind of all together. So in the context of multi-hop reasoning, then to some extent, you need the model to first be able to learn k-1 hop, and then it can gradually climb this ladder and start to learn k-hop reasoning and so on. So this is what people call hierarchical feature learning. So you need the data to be not only consisting of h-hop data, but also not only k-hop data, also k-1, also k-2 until 1-hop data. You need all of them to be present. Okay. So, but this is only the kind of naive reason for what needs to be done for hierarchical feature learning. That is, you need to have the data to be of different levels of difficulty. But what turns out to be very hard, and I think I would say 99% of the maybe deep learning researchers don't really know, is how in the end of the day does deep learning perform hierarchical feature learning. So once you have this data, how exactly does it actually turn from a feature, turn from some features for the k-1 hop into the features to support k-hop reasoning? So this was precisely what our theory work explained. That's a very deep math paper, but today I'm going to explain everything to you without any math. That is, over there we discovered a phenomenon that we give it a name. We call it backward feature correction. That explains how exactly deep learning perform this kind of hierarchical feature learning. So let me explain. So to begin with, everyone knows that layer-wise training doesn't work. Okay, in the context of multi-hop reasoning, for instance, you can first train a 10-layer transformer to learn the task of k-1 hop reasoning, and then if you freeze those 10 layers and add 2 more new layers, and then suppose now you want to fit the task of k-hop reasoning, can you do that? No, a solid no. You can try this at home, and almost no matter how much you train the 2 layers, it's not going to work. Maybe it's going to give you a little bit of accuracy, but it's not going to generally solve the problem. So in the end of the day, you have to really train all the layers together in order to learn this k-hop reasoning. So what is happening here is because if you're training all the layers together, then this gradient flow, the backward gradient flow is going to actually help you to backwardly fix the features of the intermediate layers to actually become something else, something that I call a k-1 hop, but plus a little bit epsilon. So this epsilon is absolutely important. So let me explain. So suppose you only fit the task of k-1 hop reasoning for the intermediate layer, then because all you need to do is to answer what is the next token, right? Next token prediction. So therefore, like you may be overfitting, and therefore like you may be already forgetting at this layer like many of the important information. For instance, what is K, right? For instance, like am I inside like a query or inside an answer? Like where am I in the sentence? So you may like already like miss many of the things. You may already forget many of the things just because you're only fitting the task of K-1 hop reasoning. But in order for you to perform like K-hop reasoning, you have to carry around such information. You have to carry around like what is the value of K to be the very least. So therefore, like after, for instance, the first turn layers, like for instance, overfit the task of K-1 hop reasoning, but now suppose you train all the layers together. This gives you an opportunity to backwardly fix the intermediate features to start to include such useful epsilon. And only after doing that, you can do K-hop reasoning. So this kind of what we call backward feature correction was actually at the heart, at the core of like how deep learning can perform, deep learning. That is how it can do this hierarchical feature learning, just because of the backward feature correction. And we explained actually in that work that how does backward feature correction happen? It requires actually two things. The first is what I already described. You need the data to have this ladder. You need to have hard, medium, and easy data. But the second thing that turns out to be very important to support backward feature correction is to have the residual link, the Chi-mean residual link or the ResNet kind of residual link. So this turns out to be important because it makes kind of the gradient flow to more smoothly and to go backward, so that the training can kind of learn this additional like epsilon kind of feature much faster than before. So that was in the prior work. But what we did not discuss in the prior work, just because the prior work was studying like feed-forward network, not language models. So what needs to be done for language model to support this? Actually, it requires a third thing. Think about it. When you're having language models, you want the backward feature correction to happen diagonally. That is, not only you want to fix the feature of the previous layer, you also want to fix the feature of maybe the previous token, just because I want to maybe get better prepared for what I want to answer for the next token. So there's also this time horizon. And therefore, a third thing that's going to make backward feature correction to go much faster is precisely our Canon layers. That is this kind of horizontal information flow. So adding the Canon layers is just like adding the residual links, but in this like time horizon, and it's going to make this backward feature correction to go much faster. And this is precisely why, like you can see, for instance, here, then how like the Canon layers allow like the hierarchical feature learning to go much faster than as if you don't have the Canon layers. So therefore, like we conclude here that Canon layers really speed up hierarchical feature learning, and how it speeds up is explained by this picture. So this is what we call result 2.1. Now let's move to result 3. That is, inside result 2, I just told you that on top of rope, if you add Canon layers, this is how much the performance changes. But now how about nope? So nope is this idea, the so-called no positional embedding. That is, without this rotary positional embedding, you just use the vanilla kind of transformer architecture. So this is known to fail like very badly, and we can also show it in our synthetic playground, without any doubt. But here comes the really interesting question. That is, suppose on top of nope, you add the Canon layers. How does it perform? So I'm going to tell you that the performance is extremely well. Okay, it really transforms nope to a very strong performer. So only like in one of the tasks, it's going to perform weaker than rope. But there's a reason for that, because this is our structured learning task. It requires the model to be able to understand, for instance, how far away like two tokens are. So therefore, like positional embeddings still like start to kick in and to play some role. So therefore, like without positional embedding, then you're going to perform a little bit worse here. But in all the other tasks, nope plus Canon is really performing extremely well. So this, I claim, is a really great news if you work on length generalization. So let me explain. So people really hate rope for a long history of time, because rope is known to be a bottleneck for long context anything like information retrieval. So therefore, people really wanted to use nope. but they couldn't because the performance is bad, right? So people have been trying to propose, fixes on top of nope to make it perform better, but without using rope. So let me mention two of the important works. So one of them, the highly cited work of the alibi attention, does the following. So you first compute the attention matrix. This is the nope matrix without using any positional embedding. And then you add on top of that, for instance, what are the relative differences between the two tokens? You add this kind of bias and multiply it by a scalar. So therefore, you add this positional bias on top of your attention matrix. So this is called alibi attention. And there's also a follow-up called hard alibi attention. So that does basically a hard thresholding version of the thing below. That is essentially just sliding window attention, but for different attention heads, it uses a different window size. So both of the works turned out to be very, very good in terms of length generalization. And for instance, hard alibi is capable of, say, being trained on the task of copying for only 50 tokens, but generalized to really 1,000 tokens. So that's extremely well. But one issue here is that this is really a simple task of, for instance, copying or associative recall. Then how about if you work on the shorter context but harder reasoning tasks? Then how do they perform? So this is actually a picture I'm going to show you on the next slide. That is alibi or halibi, for instance. They perform actually pretty bad on other kind of synthetic tasks that that are in our playground. And you really want to use this nope plus Canon. So they work much, much better than alibi and halibi, for instance, on our synthetic tasks. So this I'm going to show you on the next slide. So the second news I want to emphasize here is that this is also great news because rope also performs bad on short context tasks. So this is maybe perhaps a little bit less well known, but you can already see it from here. That is, for instance, on this task of reasoning depth, that is what is the kth successor of a node, so that's a k-hop reasoning. You see that just by replacing rope with nope, you're even getting better accuracy. So this is because actually rope can also hurt the model's performance in short context tasks. Because in many of the tasks, for instance, like information retrieval, maybe the positions don't matter that much. So therefore, forcing the model to use rope is like forcing the model to use positions. And that may actually negatively hurt your performance in many of kind of the reasoning tasks, not only here, but also here as well. So therefore, by replacing rope with nope, you can also improve the model's performance on short context reasoning. So this is, I think, maybe not quite recorded in other literatures, and we can very easily discover it using our synthetic playground. So now with all of this information, a very natural choice to study next is how about combining the both, right? How about, say, performing just 1/4 of rope, but 3/4 of nope, and then plus Canon. So this turns out to get really the best of both worlds. You get the good performance of nope, and you also get the good performance of rope here for the structure learning task, and also it's going to improve the model's performance on long context information retrieval, for instance. So here, by 1/4 of rope, I mean many different versions. So we actually tested 3 of the versions. So we give them different names, like quarter nodes or 2/4 nodes or 3/4 nodes. So the three of them correspond to, say, having 1/4 of the attention heads, each of them doing rope and the remaining doing nope. That's version number 1. And version number 2 is having half of the attention heads, each one of them using half of the dimensions of rope. The third one is having only having all the attention heads doing rope, but each one of them only doing 1/4 of rope. So you can have all those different variants. They turn out to have very similar performance. So therefore, in the end of the day, what really matters is that once you have the Canon layers, this allow you to significantly reduce the usage of rope. So without Canon layer, you can't remove rope. You can't reduce the usage of rope. But with the Canon layers, this gives you the new opportunity to significantly reduce the usage of rope, and therefore to get even a better performance in many of the dimensions. So this is our result number 3, and this is the overall performance gain you can get just from the original rope. And we are also going to revisit this like in the last result, result 12, at which point we're going to see that in real-life pre-training, like on the academic scale, you're also going to see the same phenomenon. That is, this is the final kind of architecture choice we are going to advocate in terms of transformers. So in the next result 4, I'm going to perform some ablasive study for Canon on transformers. So for instance, I'm going to show you like where to add such canons and what format of the canon do you actually want in order to get the best performance. The first result we obtained is actually what I promised a few slides ago, that is the residual format of the canon is absolutely crucial. So you really want to have this H+ kind of thing. So in order to see this, we did some very comprehensive ablasive study, like for NOPE and for ROPE. Just to zoom in for one of them, for instance, this task. This is the so-called knowledge manipulation task. And here, like you have 9 rows, and each 3 of them in a group. Say those 3 rows correspond to 16 hops of knowledge manipulation. And this row corresponds to like using the residual version of the canon, and this one corresponds to using the non-residual version of the canon. You see like it's generally like perform much worse than using the residual version. And we also tested using the residual version, but with activation. And its performance is also bad. So it doesn't seem to be necessary for me to add any activation either. So therefore, like we recommend this like residual format of the canon in the end. So that's how we did the first ablasive study. In the second ablasive study, we basically study like how much canon do we want to add. So it turns out that adding any one of the canon, it could be canon A, canon B, canon C, or canon D, that's generally like already much better than, for instance, the original transformer. So this is the performance of NOPE, but you can see it similarly like for ROPE or for other synthetic tasks as well. But overall, like in the end of the day, it's the more canon, the better. If you do like canon ABCD, the full score canon, or you can do ABC, or even AB, or even ACD, or even BD. Those performances are generally better comparing to just adding one canon alone. Okay. So therefore, like this is another task. You see that also like ABCD and AC or ACD are better than like A, B, C, D alone. Okay. So therefore, it's the more canon, the better. So this is actually another place that for me to show you this result I promised a few slides ago that corresponds to alibi and alibi. So earlier I told you that alibi and alibi are very good modifications on top of NOPE. So they're going to indeed like improve the performance of NOPE, but they're still like nowhere close to like our canon performance on top of the NOPE architecture. So Canon, by just doing NOPE plus Canon, is going to perform like much better than alibi and alibi in all of our synthetic tasks that we designed. So this is actually, something I'm going to like reiterate a few times today. That is, it's absolutely important to design a versatile pre-trained playground. So if you only focus on, for instance, associative recall, or if you only focus on, say, long context, yes, you may get some improvement, but maybe like you're going to miss the improvement in some other dimensions of the skills. Okay, so therefore, like once you use a versatile pre-trained playground, you can truly see, for instance, the benefit of doing Canon over, for instance, alibi and alibi attentions. So the third ablasive study I'm going to do is regarding this Canon B design. So I want to emphasize that Canon B is insufficient. So let me explain. So I showed you this folklore that is associative recall needs 2 layers of attention, right? So therefore, this is something that's well known like among researchers, and people have been thinking about really how to repair attention, how to change it so that this only recalls 1 layer of attention. So one such work is, for instance, from my colleagues at the fair in Meta. So they proposed this what they call multi-token attention, and it's extremely well like in terms of the performance. And for instance, it can just make sure like this associative recall can be implemented just using 1 layer of multi-token attention. So that's nice. So that's an architecture kind of change on top of the attention. There's another work, the Primer work, that I discovered after actually the paper appears online from Google. So they actually introduced something similar, but much simpler than the multi-token attention, which is to add actually just Canon B. Okay, but without the residual link. So they introduced this as a way to fix a attention layer to make it to enable it to perform basically like associative recall, for instance, with a single layer. But in our playground, you can test this, their idea that it's, yes, giving some improvement on top of the original transformer, the original rope, but it's still like nowhere close to our like Canon ABCD design. So therefore, like this is a place I really want to emphasize the following: that is, Canon is not tied, for instance, to the attention or MLP or any specific architecture layer. So we even tested, say, Canon ACD or ABC. They already perform extremely well, say getting like 90% of the performance of this final row. So therefore, like if you want to fix attention, you don't need to touch attention. If you want to, for instance, fix MLP, you don't necessarily need to touch MLP. So the kind of overall like really beautiful thing about Canon layer is that it's an independent kind of architecture design, orthogonal to any of your architecture kind of smart like architecture innovations. So you can add it anywhere. You can add it even outside the attention. That can also fix the issue of this multi-token attention, of this associative recall. Okay. So those are like the ablasive studies we did here for Canon on transformers. In the next result, I called result 5, I'm going to show you that the same synthetic playground also supports even finer architecture comparisons. So let me give you like 3 examples. The first example is about like the gated MLP versus standard MLP. So that was introduced by Noam Shazier like back to 5 years ago or 6 years ago. So he discovered that by changing the standard MLP into this gated format, then this actually improves the model's performance in real life, some real life benchmark a little bit. So therefore, since then, it became actually what people use inside at all of the frontier models. And we can also observe the same using our synthetic playground. So this means that our synthetic playground can actually reconfirm, for instance, some of those previously discovered architecture finer kind of necessities, such as like changing from standard MLP to gated MLP improves the model's reasoning, and we actually can see like how much reasoning does it improve, like a tiny bit, but still like noticeable. So that's like a simple reconfirmation of some prior work. And another reconfirmation of the prior work is the following: that is, in this same like premier paper, the Google researchers discovered that replacing the CLU activation with the ReLU-SQL activation also improves the reasoning, and we can also like confirm the same. That as you see, like for instance here, like it's becoming like much brighter here. So therefore, like you already see that our synthetic playground is very good in terms of even like telling kind of apart very finer architecture differences about which one is better. But those are only the prior works, right? And now like there's a very interesting question, on this table. That is, what about here, right? If ReLU-SQL is better and if gated MLP is better, why don't people do gated MLP with ReLU-SQL activation? So this is our new discovery. We showed using our synthetic playground that it's actually not going to be better. So if you do ReLU-SQL, it's going to hurt your performance on top of gated MLP. So in the end of the day, it's either or, like you either use gated MLP or ReLU-SQL, but not both. So this is what we summarized as result 5.1, that is ReLU-SQL activation. It slightly improves the model's reasoning on standard MLP, but actually it slightly decreases the model's reasoning on gated MLP. So this is something that you can very easily discover using our synthetic playground without running like super large scale models in real life data. In the next result 5.2, it's still like about MLP versus gated MLP. So I told you that it's going to slightly improve reasoning, but at the same time, it's going to actually reduce knowledge capacity by about 30%. So this we discovered actually in our prior work, part 3.3. That is, if you do gated MLP, this is how much knowledge you can store. And if you use standard MLP, like you see that it's actually 30% better of knowledge you can store. So this is like log scale. So therefore, like this curve, this line versus this line is already 30%. So the reason for that, we actually studied very closely in the prior work, is because making the MLP like gated is going to make the training actually a little bit unstable, and therefore like it's actually learning the knowledge slower than before. So that was the cause for this capacity drop. But now comes the interesting new result, that is adding the Canon layers actually can recover like half of this capacity loss. That is, if you do say gated MLP but plus Canon ABCD, you can get this green frontier line that's kind of in the middle between the two. So therefore, like you can get back about 15% of the knowledge capacity. So the reason for that, once again, is because Canon layers improves the learning speed. It improves the hierarchical, feature learning speed, but therefore, like ultimately the learning speed. So therefore, like by going to gated MLP, you're decreasing the learning speed. But now adding on top of that Canon layers, it improves the learning speed. So that was the cause for how you can get back to half of the model's knowledge capacity. That was result 5.2. And in result 5.3, we studied MOEs, mixture of experts. So mixture of experts is widely known, to improve the model's speed on inference, because during the inference time, it only needs to route using one out of the experts. For instance, if you have 32 experts, you only need to go through like the path of a single expert. But at the same time, people also understand that this is going to decrease the model's knowledge capacity. So for instance, if you have like 32 experts, then in the end of the day, how much bit of knowledge you can store per parameter actually drops by a factor of about 2. Okay, so this is understandable because nothing is perfect, right? By just during the inference time, you're only using one out of the experts, and you can't imagine that all of the experts are kind of you can't imagine that the model is like having the same knowledge capacity as before, because you're only using some very sparse routing during the inference. So therefore, getting actually a factor of 2 loss in knowledge is already super great. You're not getting like a factor of 32 loss in the capacity. And now comes the new result, that is adding Canon layers. You can actually improve this capacity by another 25%. You can once again recover this loss a little bit. So this time, very importantly, I'm testing only Canon ABC. I'm not adding the Canon layers inside MLP. You can also do that, but that requires you to change a little bit the code for the MOEs, but maybe you don't want to do that. So therefore, just by adding Canon ABC, you can already see this kind of very good performance gain in terms of knowledge capacity. So overall, I just showed you 3 examples about such much finer architecture comparisons that are also supported by our synthetic playground. So this is really a good point for me to summarize, that is, doing synthetic pretrain will really allow you to save a lot of money on the real-life ablations, and you can discover things with much smaller scale and much faster. So this actually summarizes results 1 through 5. That's about Canon layers on top of the transformer architecture. And now in the next set of results, let's look at linear models. So linear models include, for instance, linear attention or Mamba or Gated DeltaNet and so on. So let us start with linear attention. So what is linear attention? So let me remind everyone, whenever you're doing full attention, you multiply this query and the key matrices together, forming this L by L square matrix, and L is the sequence length. And therefore, you can perform a softmax per row to basically allow the full attention to very precisely determine from if I want to attend to the current token position, which pieces of information do I want to read from the previous tokens. So that was how full attention works. In linear attention, you do this oppositely. That is, you merge the key and the value matrices. You multiply them together and forming a much smaller matrix of only dimension d by d. So this serves as a memory to the extent that in the new time horizon t, whenever you see new vectors, the key vector and the value vector, you just add on top of your memory this rank 1 update, key transpose v. Okay, and that was how it works. So linear attention, because it doesn't allow the softmax to be included. For instance, you can still left multiply your memory module with a query vector, but you cannot perform softmax like before. So this was why its performance is generally worse and much worse than the full attention. But there's a recent kind of upgrade of linear attention, the so-called gated linear attention, like joint work from MIT and IBM research. So they introduced the following, that is, instead of doing this, which is always adding things to your memory, they also allow you to be a little bit forgetful on your memory. So those parameters, alpha t's, are kind of trainable parameters that depend on your hidden state, so that you can like dynamically decide if I want to, after seeing the current token, do I want to, for instance, forget a little bit about the history or not? So therefore, like you can have this scalar that are multiplied on top of the memory before like you add this new piece of knowledge. So this is called gated linear attention, but it also doesn't perform well. So we actually tested it in our synthetic playground. It's actually performed very well in terms of knowledge capacity. It's much better than the transformer, but it's still like generally like worse in terms of reasoning. It doesn't matter if it's in-context reasoning, these two, or if it's knowledge reasoning or structure reasoning. So for all of them, the performance is bad. But this was only the beginning of actually a very, very long journey of research. And there exists like more than hundreds of works that study like how to build like better linear time architectures. So two of them I want to emphasize today are the Mamba2 architecture and the GDN, because they underpin today's largest open source hybrid language models. So Mamba2 actually was used by, for instance, NVIDIA's Nemotron 3 architecture, and the GDN was used by QuanNext and as well as by Kimi. So that's why I picked those two. And you can also test them in our playground, and you see that they are much, much better in terms of reasoning. But now comes a very, very interesting result I derived. That is, how about adding the Canon layers on top of GLA, on top of this gated linear attention? So the Canon layers, not only work for transformers, you can add it to any architecture, for instance, the linear attention. And it turns out the performance will, significantly boost to an extent that you can quantify them, but to an extent that this even beats Mamba2 and also performs like on par with GDN. So we really summarize this as result 6.1. That is, Canon really lifts linear attention to match GDN and outperform Mamba2 just by doing this like very simple architecture change without any kind of smartness about how I need to redesign my my linear attention and so on. We also did a bit of ablasive study on top of GLA. Most importantly, the original GLA authors, since their paper publication, they also proposed to add a Comp1D layer similar to our Canon B. So their Comp1D is a bit different. So they actually added the activation and without residual like we did in the paper. So the rationale, if you allow me to guess, like why they try to introduce this after the paper's publication, is because they also thought about, linear attention is weak, then can I maybe introduce this horizontal information mix to support some type of multi-token attention? So we also tested their version, the GLA plus Comp1D, in our playground. So it's giving you some improvement, very strong improvement over the original GLA, but it's nowhere close to our full Canon version of the GLA. So therefore, like for a weak backbone, like the linear attention architecture, you really want to turn on as many Canon sublayers as possible. So this is our first ablasive study result. The second result is that we ultimately recommend this configuration that we call Canon A, B, C, D, but with little b. So here, we use Canon little b to refer to their original Comp1D design. That is the one with the activation. So there are two reasons we do this. Number one is that this activation is actually not really related to the horizontal information flow. It's actually related to linear attention. So linear attention is linear, and therefore people have proposed ideas to add feature maps on top of it, or equivalently adding activations. So if you do Silu activation, so that becomes basically a non-linear version of the linear attention, but with feature map being Silu. So therefore, adding activation actually helps. But another reason that we, use their original Canon little b, that is the version with activation, is because we trust the original authors in terms of maybe they did already some ablasive studies about choosing what are the best parameters, but also it allows us to perform a much stronger comparison. For instance, on top of this Canon little b, we add. We are not replacing anything. We're adding new things. We're adding the Canon ACD, the residual versions of the Canon. This is actually what I'm showing here. And after adding the ACD, you see this continued improvement. So this is a strong signal that the original kind of Comp 1D or the original what I call Canon little b design is not enough. Okay. So in the end, we recommend this Canon a little b CD. And this is another place that I will emphasize the same thing as before, that is Canon is really not tied to the attention layers. You can add it to Canon B. We even tested the Canon ACD alone without B. That also works extremely well. Not as good at this, but definitely better than the original Comp 1D. So therefore, Canon is really not tied to the attention layer. And the final kind of small result we did here is that we also tested Canon layers on top of other different nonlinear feature maps. Like one of the popular choices in the old days was the Illu +1 activation. We also tested and Canon also works over there and so on. So overall, we did this ablasive study on top of GLA to show that you want to add as many Canon layers as possible, and we recommend this configuration of Canon a little b CD. In the next result, let me show you about Member 2. So I showed you already the performance of Member 2. But now let me tell you a secret behind Member, actually both Member 2 and Member 1. So they have this very smart SSM design, but outside the SSM, they also secretly kind of introduce this Comp 1D layer, similar to, similar to our Canon B, but on selected coordinates and without the residual link and with activation. So this was inherited from their predecessors, Member 1 and H3. But now comes a very interesting experiment with it. That is, we tried to remove that Comp 1D. And then the performance of Member 2 just significantly dropped to just as low as GLA. Actually, even a little bit worse than GLA. But if on top of that, you add back all of the Canon layers like Canon ABCD, then you can continue to see a performance gain from here to here. So therefore, this is actually a place that drives me to think. That is, how much of Member's performance was really truly from its SSM, or is it actually mostly or all of them coming just from the Comp 1D, or the Canon, or this kind of horizontal information mix? So this is another place I want to emphasize on this picture again. That is, existence is cheap, and the learnability is everything. You can design your architecture to be really arbitrarily complex, with a lot of wishful thinking, like a very smart SSM design. But in the end of the day, maybe the Sc.D or Atom optimizer is not going to cooperate with you. It's going to learn something very cheap or very simple, such as just some horizontal information mix. Okay, so that's our result 7.1 on the Member architecture. And we call it a secret behind Member 1 and Member 2 models. In the next sub-result, I'm going to perform a little bit ablasive study, once again, on top of Member 2. The first observation we made is that Canon also works outside the SSM. So for instance, we tried to do the Canon layers at position A, position C, and D, but without doing it inside the SSM like the original authors. And we see that its performance, this Canon ACD configuration, still performs very strongly. So therefore, Canon is really not tied to attention and not tied to the SSM design. It's really a standalone thing that it can be inserted anywhere inside your architecture. And number 2 is that we also recommend this a little b CD configuration. So little b means their original Comp 1D implementation, and ABC are our residual version of the Canon. And the third thing I want to emphasize here is that please, do not over-optimize for long context. Okay, it may hurt your performance of regular short context tasks. So let me give you one example. This was a paper that I really liked a lot. That's the so-called mimetic initialization. So it discovers that if on top of the same Member 2, or it can also be the Member 1 architecture, if you change the initialization a little bit to make it sort of behave more closely to attention, then the model suddenly performs very strongly on long context, especially on learning to record, which is the associated record tasks. So you can train the model on a short context and it lets generalize to long context. Very nice result. But unfortunately, we discovered that if you use the mimetic initialization, it hurts your performance on short context reasoning. So this is really like a place I want to reiterate this point that it's really, really important to study a versatile pretrain playground, okay, in order to like reveal like what's your architecture's true capability in all the different dimensions. Because you may be very good in terms of long context, but you may be sacrificing yourself on short context skills. So in the end of the day, you want to design an architecture that's like as good as possible in all the dimensions. That's our ablative study like regarding the member architecture. In the next result, I want to talk about GDN, the Gated DeltaNet plus Canon. So what is GDN? So in GLA, in the linear attention, the idea was to have this memory module, you scale it down, and then you add this rank 1 update. So in GDN, the idea is that you not only scale down the memory if needed, you also like scale it down by this like identity matrix minus a rank 1 update, like key transpose. So this allows you to like very intelligently decide if there's a specific piece of information in one particular dimension I want to remove from the memory. So this is definitely like smarter than the linear attention design. So I showed you the performance earlier, but I want to emphasize that the GDN also secretly has a conv1D layer inside it. And this time, if you remove it, different from Memba2, its performance is not going to drop to 0 like in all the dimensions. You still have some reasonable like accuracies on the in-context reasoning task, but not as well as like knowledge reasoning or structure reasoning. And on top of that, if you introduce like our full score Canon ABCD, you can like further improve its performance in at least like 2 out of the 4 directions. So therefore, in the end, we actually recommend Canon a little BCD once again on top of GDN, and the lesson was once again like the more Canon layers, the better. And we also tested, for instance, GDN with Canon ACD to show that it has strong performance. So therefore, like Canon also works even outside their GDN layer. So this is once again this same point I'm emphasizing again. That is, Canon layers are standalone architecture ingredients that do not need to be tied with any specific layer. It can work even outside your GDN layer or attention layer and so on. So now comes result 9. So this is actually a very good point for me to lay down all the linear architectures and compile them like side by side. So those are the GDN member and glass without conv1D, without Canon layers. So those are the ones with full score Canon A, B, C, D. So vertically, that we see that across the architectures, there are some performance differences, for sure. But this difference is nowhere close to like the amount of performance gain you can obtain just by adding the horizontal information mix, the Canon layers, right? Like horizontally, you see this huge gain, but vertically, like not by much. So therefore, we really conclude that the most performance achievable with, at least our tested linear architectures are really like achievable with the simplest like linear attention plus Canon design. So this really makes me think that maybe the current research direction of linear model architecture design may require some reevaluation, right? That is, this picture again, that is you can design an arbitrarily complex linear model, but is it really learning, the complex, the deep kind of function that you wish it to learn? Maybe it's only learning something, very simple, like the horizontal information mix. So this, by the way, I'm also going to show you that not only holds in our synthetic playground, it even scales up to very large scale. So if you do like 8 billion size model pre-trained with 1 trillion token, which I will show you in my next talk of part 4.2, then linear attention also works no worse than GDN and works much better than Memba2. So therefore, like our synthetic playground is not a toy example. It's actually a very predictive playground that can predict even much larger scale in real life pre-training. So that I will cover in the next talk. So this concludes actually our discussions about Canon layers on top of linear models. And in the next result, let us actually compile linear models versus transformers. So this time I'm going to add Canon layers to all of them. So for transformer, I took this like quarter rope version that I call it the quarter rope plus like 3/4 of node. I use this quarter node to denote it, and I add on top of that the full score Canon ABCD. And for the linear models, I add this Canon A little bit CD as I introduced earlier. So this is very important because it allows me to perform an apple-to-apple like fair comparison across architectures. So this can really reveal the true architecture differences. Because if you don't do this like alignment, then if you just look at the vanilla like transformer or the vanilla GLA, they did not have any of the horizontal information mix. But if you look at GDN or Memba2, they already secretly had this conv1D layer. So they have some horizontal information mix. So therefore, actually, if you compare the models without this alignment, without adding the full score Canon, actually, I showed you the result in the previous video, and I warned you over there that it's not a fair comparison. You may get some misleading result. So this time, I want to add all the Canon layers and now compare the models. So in our 5 synthetic task directions. So for 3 of them, I claim that the differences are actually not that big, but still like quite noticeable. So let me mention 2 of them. So in terms of structure learning, we see that transformers are generally like a bit better comparing to the linear models. The linear models are similar, but transformer is better. So this is understandable because the structure learning is a task that requires the model to perform some very long-range kind of structure ambiguity detection about how to parse the sentence and so on. So this requires the model to perform some computations on like how far like a token is to me, or is it like close to me, and so on. So therefore, like the positional embedding plays an important role. So that's where like the full transformer actually is beneficial because it allows you to perform like more precise like token-to-token information flow. And the linear models are slightly falling behind. And the other thing worth mentioning here is that the Memba2 architecture is actually very bad in terms of reasoning breadth. So this is a task that requires the model to perform like a tree-like search in terms of reasoning, and it seems like Memba2 is just not good at it. So this is also reflected in real-life pre-training. So in the next talk, like part 4.2, I'm also going to show you that Memba2 is not so good like in real-life tasks as well. So therefore, like I think there's a reason for why this happens. But those 3 are actually the smaller kind of differences. The biggest difference happened in the remaining kind of 2 directions. So one is this dimension of models' knowledge capacity. We actually measured that the linear models are very close to each other, and they're generally like 40% more. They can hold 40% more knowledge comparing to the transformer architecture. So this is actually the full result. So if you do the transformer, this is the frontier line. But if you do like linear models, it doesn't matter if it's Memba or GLA or GDN, the performance are generally like 40% more knowledge comparing to transformer. So this is actually a very big difference. Another even bigger difference we discovered is actually here in terms of the reasoning depth. So there was the task, remember, about answering what is the kth successor of a given node. And it turns out that transformer can perform like 16 or 8-hop reasoning, but linear models just cannot. So some of you may find this like contradictory to the slides I showed you earlier, because the slides I showed you earlier were like for 4 or 2-hop reasoning. So the linear models can perform maybe at least GDN like quite well on 4-hop reasoning, but not really for 16 or 8-hop reasoning. So therefore, like we summarize as the follows: that is, linear models can hold 40% more knowledge, but transformers can reason 4 times deeper. So this can be very cleanly seen like using our synthetic pre-trained playground. In the next result, I want to dive into this part and show you like why exactly did this happen? Like why does linear model like perform so shallow in terms of reasoning? So some people may think that this is because linear models have like limited recurrent memory. So this whenever linear model performs bad, like people usually like criticize it by just saying that, oh, because it's a recurrent model, so it has a like memory limit and so on. But today I want to emphasize that it's totally not because of this. So here, for instance, in this reasoning depth task, the length of the sequence is only around like 1,000 tokens. So we can in fact prove it that the recurrent memory is much more than enough for you to hold the entire piece of information about this entire context of like which node connects to which node, for instance. So I can give you at least two proofs. Proof number one is that the models turn out to be able to perform one-hop reasoning, which is one-hop information retrieval, and therefore like definitely it can memorize. It has enough recurrent memory to actually know the entire history of the tokens. So that's proof number one. And proof number two is that you can mathematically compute for each of my layers. It can be GLA layer, it can be Mamba2 layer, or GDN layer. Then the size of the recurrent memory turns out to be 100 times more than enough to store the entire sequence of knowledge. So therefore, like, it's not really because of the recurrent memory. It's because of the following. That is, GDN, for instance, it doesn't matter. It can be GLA or Mamba2. The plots will be similar. So all of them actually perform very slowly in terms of one-hop reasoning. But in contrast, for instance, transformer, it learns like one-hop reasoning very fast, and not to say like two-hop and three-hop and so on. So therefore, we summarize that linear models really like struggle in terms of deep reasoning because it's very inefficient in terms of compressing and retrieving information from the context. So if you remember, like the Canon layers are good at hierarchical learning, right? It's going to make the model kind of learn from one hop to two hop to three hop actually faster. It climbs this ladder faster. But if the base model is already very bad in terms of one-hop reasoning, then just adding Canon layers doesn't help anymore, right? You have to really like improve the one-hop reasoning for linear model. So this really pinpoints to the exact weakness of linear models for future research. And until this issue is resolved, then I claim that hybrid models remain essential if you want the model to ever perform this kind of deep reasoning tasks. So this is result 11, where like I showed you like why transformers can reason deeper than linear models. So in the final result 12, I'm going to actually perform some real-life pre-training to actually show that many of those synthetic discoveries actually echo very well in the real-life pre-training settings. So I'm going to perform real-life pre-training at what I call the academic scale, which is I'm going to focus on models of 1.3 billion parameters pre-trained for 100 billion tokens. So this turns out to be the largest scale that people usually do when they're performing like architecture research in open literatures. So people use, for instance, the Slim Pajama data, or maybe the Fine Web EDU data, or maybe like nowadays also the Nematron CC data. But actually, it doesn't matter which one you use. So here in this talk, I'm going to use the Slim Pajama data. In the paper, you can find Fine Web EDU as well. So all of the like real life results are actually summarized in this like gigantic table, and it contains a lot of information. I'm going to read this like to you very carefully and very patiently. So there are two blocks of models. The first block are the block of transformers, and the second block is the block of linear models. So maybe Mamba. So here Mamba can be either the one with MLP layer or the one without MLP layer, or it can be GLA, it can be GDN. And there are four like column groups. The first group is the group of so-called discriminative tasks. So those are some very like well-known like benchmark names like ArcEasy, ArcChallenge, or HelloSwag. So in each of these tasks, it's a multi-choice question, like 4-choice question, and the model is given like a context. Then like it's given, then followed by one of the 4 choices, and you read like the model's log likelihood to determine if the model prefers answer A or answer B or answer C or D, and then you compile that to the correct answer. So that's what people do as the so-called also so-called like zero-shot performance evaluation. And the second group of tasks is the set of like generative tasks. So here, for instance, I can give the model like a context about the Titanic, and then ask a question like, who found the remains of Titanic? And the model has to word by word correctly answer the name, that is Robert Ballard. So this is generally like a harder task than the one to the left, because the model has to word by word perform this answer. And because of its difficulty, then people have proposed the so-called like just read twice, the JRT procedure. That is the simple idea of repeating the question and repeating the context and question twice before the model answers. Okay, so this way the model is going to answer with a much higher accuracy. And for instance, I use trivial QA2 to represent that I'm repeating the context twice, but trivial QA is the one without repetition. So I'm testing both the ones with and without repetition. So this is the set of generative tasks. So the other two sets of columns I'm going to actually talk about a few slides later. Those are our own designed versions of the one-hop or two-hop reasoning benchmarks. So let's focus on the first two columns first. And the first set of results I want to emphasize here is that if you just use the vanilla like llama or the rope architecture, and just by varying the random seed, like say 8 different times, you can see already like it's very noisy. The performance on those benchmarks are like really varying a lot. So this was actually the same picture I showed you in the previous talk. And over there, I emphasized that the real-life pre-training is really noisy. And therefore, like if you want to really derive some robust and kind of meaningful result, you have to look at the rows that are kind of outside this standard deviation of the random noise. So for instance, the following 4 rows are clearly kind of outside this random noise band. So those are actually the 4 rows corresponding to GLA, the linear attention, the original linear attention without comp1D, or these two correspond to the Mamba without comp1D, and this one corresponds to NOPE, the original NOPE design. So those are exactly what we showed in result 3, 7, 6. That is like Mamba2 or GLA without comp1D performed badly, and NOPE also performed badly in its original design. But the beautiful thing here is that if you use real-life pre-training, you see, for instance, this accuracy of maybe 42% versus like in general, you get like a 52%. So therefore, like you only see a difference of 10% of the accuracy change. But in our synthetic playground, you see things like with a much stronger contrast. It's like almost 0 versus 100% accuracy difference. So therefore, like this really calls back to our result 3, 6, 7 that confirms many of our findings from the synthetic Pretrain playground. The next set of results I'm going to read with you is regarding our own design of the one-hop reasoning. So we designed the task as follows. We give the model actually 5 sentences about 5 random people. So we generate the people's name like using random English names, and then like say like they were born in some randomly chosen years, and then we ask the model in the 6th sentence like which year was one of the person born in, and we then like bury those 6 sentences into a randomly chosen Wikipedia passage of L tokens, and here like L is between 0, 1K, and 6K. So 0K, 1K, and 6K. So we used this task as our reference for this, what I call like one-hop reasoning, or you can call it one-hop information retrieval. So some other people use maybe the needle search or the phone book. I personally don't like them because they're too easy. So you're giving the model, for instance, a randomly generated phone number, or maybe like a special like number in the needle search. So those are so special, so that the model, it gives like the model a very strong signal to say, oh, you have to memorize it. But here, like we are like talking about something more natural, like the people's birth years. They're very natural because in the pre-training you see a lot of them like in the Wikipedia, people's biographies and so on. So the model definitely understands what are the years, right? And also like some other people like use the Babylon task. We don't like it. We also showed it in the paper, by the way, but you can't read too much from it. So it's too hard as a task because it requires the model to perform like many like factual reasoning and so on top of that. So we picked our like own like simplest possible one-hop reasoning task. And here for this task, you can already like see something that's for instance well known like in practice, that is rope. The rotary positional embedding doesn't length generalize. So we pre-trained all the models equally like with a 4K context length, but you see that if you use just rope, it does not length generalize to like 5K or 6K. But you also see like those like 4 good rows. So those are precisely the first 2 rows are precisely the quarter of rope, this one, and the second set of them are precisely the NOPE. So we see that doing like NOPE or reducing rope actually helps the model to perform well on long context. So this actually calls back to our previous result. And by the way, one of the rows is bad because that's the original nope. So therefore, the only 3 good rows are actually the following 3, but they correspond to exactly this nope plus canon or the quarter rope plus canon that we predicted from the synthetic tasks. So this calls back very well to our synthetic result number 3. So the next set of results I want to read with you is regarding this block. So you see that it's quite dark comparing to the full transformer. And we summarize this by saying that linear models really struggle on even short context retrieval tasks. So let me just focus on maybe one of the columns. This is exactly this birth year retrieval task I introduced to you. But this time I'm picking L to equal to 0. So I'm having just a total of 6 sentences, and the model needs to retrieve one of the 5 birth years. So this is only a total of like 100 tokens, around 100 tokens. And it turns out all the linear models already start to struggle here after this scale of the pre-training. In contrast, like full transformer is extremely well, like 99 point something accuracy. So if you're a practitioner and you see this for the first time, you may be surprised. But if you have watched my full talk, at this point, you should not be surprised because result 11 already predicted it so. That is, linear models, not only GDN, but all the linear models actually struggle in terms of one-hop information retrieval. And this is exactly, what in real life it performs. So this is how it calls back to result 11. And the next result I want to point out here is actually this very bright row. And if you read the name, this is actually GLA, the linear attention plus Canon, right? So I predicted using synthetic tasks that just by using the linear attention, and once you add the Canon layers, it performs no worse than GDN or Mamba2. And here, like you see it. And some people may already use this table to conclude that GLA plus Canon performs the best among all the linear models. But I don't want to overemphasize on that because we have a lot of random noise. So therefore, I just want to say that it's no worse than any of the other linear model configurations. This calls back to result 6 plus 9. And the kind of final block of things I want to read with you is this two-hop reasoning. So this is, once again, our own designed tasks. So here, we give the model 3 random persons born in 3 random years, in natural English sentences. And then we also tell the model a bipartite graph from 3 new people matching to the previous 3 people. So we say that maybe Y1 was born in the same year as X3 and so on. Then we ask which year was one of the Y people born in. So a total of 7 sentences. And we once again bury this into a Wikipedia passage of L tokens, so between 0 and 6K. So now you see that, excuse me, even if L equals to 0, then all the models perform extremely bad here. Just almost like random guess, because random guessing would be correct with 33% accuracy. But all the models, regardless of if it's transformer or linear model, they all fail. And this, in my mind, is the simplest two-hop reasoning task. So there's a reason for this. I actually mentioned this in the previous video, that is real-world data is too skill mixed and it delays many of the emergent skills. And in this case, even two-hop skill, it cannot be learned at this scale of the pre-training. And this is really the absolute important, the point that I want to emphasize on the absolute importance of using our synthetic playground. Because in the synthetic playground, you can stress test your architecture's capability. For instance, in terms of 16-hop or 8-hop reasoning. But in practice, maybe you pre-trained using a large model for a very long time, but you're only testing it on some very naive scale, only 1-hop. Maybe you're never even testing it in terms of any of the 2-hop reasoning skills. And therefore, if you use real-life pre-training, how would you be confident that you're designing an architecture that works better than the prior work and so on? So in the last slide, I just want to say that I will stop reading new signals from this paper because beyond this, I think it's pretty much noise. So in particular, at this academic scale pre-training, you already see that, for instance, what we predicted as rope plus Canon versus rope, we said it's much better than rope, but you cannot see it from here. Like the rows will be like pretty similar. And also you cannot see, for instance, how much better GLA plus Canon is comparing to like GDN or Mamba 2. So those actually I will show you in the next video, part 4.2. Over there, I'm going to perform much larger pre-training tasks, 8 billion size model and pre-train for 1 trillion token. And I'm going to not only confirm those results, I'm also going to show you some new lessons over there. So finally, I just want to conclude by saying that synthetic pre-training really saves money. And not only saves money, it can also give you more accurate predictions that typically you cannot even observe in such kind of academic scale pre-training. So those are the results, like 12 results divided into 2 separate videos. And I hope you have liked it and see you in the next talk. Thanks for watching.